All right. I will begin with a word of prayer once I get up here. Heavenly Father, we thank you again for your creation and our ability to study it, and just pray that we would glorify you what we do and understand a little bit more about how to solve differential equations. Lord, in my prayer, Lord Jesus. Amen. All right, so we have, in some sense, exhausted the nice problems that are available in this course. Like, Test 2 really covers the prettiest part of the material in some sense. I personally find the material that you guys were just tested on to be by far the nicest and most simple part of the course, I think, as a whole. I mean, there are still some nuances, for sure. Like the whole annihilator method and sorting through what's the particular versus, what's the right form of the particular. That does take some studying, and I'm sure some of you probably weren't quite done studying that. Usually the case. 93-35, but there's still the final. So I guess I should tell you after I turn back Test 2 that I still will drop not just one, but actually 2 tests if your final exam score is higher. So there's still hope, even if something went terribly, horribly wrong on Test 2 and Test 1. But you do need to do your homework, because I won't fix that for you. All right, let's see here. So,
can you double check the top hat code? Because it is not.
It says it's wrong.
There we go. Thank you. So today I want to talk about power series. Or more generally, series solutions. To second order ODEs. So guys, something funny happens here, in some sense, because technically speaking, the technique I'm going to share with you guys, we could actually equally well apply to third order, fourth order, fifth order, whatever order differential equations. Even systems of differential equations could be solved using series methods. It's just the custom of this course to only talk about pretty much either the second order or the first order case with this method. And so I will follow that custom because it's more than enough to confuse the students, which is of course my main goal. So let me just set up for you the problem. Our goal is to solve, let's say, p of x times y prime prime plus q of x times y prime plus, I don't know. Let me call these p and q. Let me call this like I'll call this A2. I'm going to call this A1. And then A sub 0, function of x possibly y, equals to, let's say, g of x over here, all right? So here, where A2, A1, A0, and g are all functions of x, generally speaking, right? So it could be that they could be constant, right? So like up to this, what did we cover last part of the story, last story arc of the course? These weren't functions. G was, we could let g be a function, right? But the A2, the A1, and the A sub 0, these coefficients were constant, right? That's the problem we've solved up till now, the constant coefficient case. But now our coefficients could be functions. By the way, a bit of terminology that we should all know is that this, if there exists, let me say it this way, if there is even one point at which, let's say, g of that point, x1, is not equal to 0, then g is not identically equal to 0. And this is a non-homogeneous problem. This is what this word means, non-homogeneous. On the other hand, if g of x is equal to 0 for all x, then this is a homogeneous problem, meaning homogeneous. So that means not homogeneous, all right? That's the terminology. This is important because we expect different kinds of solutions, whether we're in the homogeneous or non-homogeneous case. Now, the good news is that, generally speaking, the theory, if you will, theory says that y will be equal to c1y1 plus c2y2 plus yp, right? Where we have like a2y y sub j prime prime plus a1 y sub j prime plus a sub 0 y equals to 0. And on the flip side, we have a2 yp prime prime plus a1 yp prime plus a0 yp prime equal to g. Right? So this is what we're looking for. We're looking for a pair. This is for j equals to 1 and 2. We're looking for a pair of linearly independent fundamental solutions, right? You can take a linear combination of those, and that gives you the homogeneous solution, right, which is this piece. And then we are looking for a particular solution which actually reproduces the forcing function g, right? If there is no forcing function g, if g is equal to 0, you have to find a particular solution, right? That's not part of the problem, right? So there's a little bit more that enters in here. So here's the deal. Definition. Let's see here. F of x is analytic at x naught if f of x is equal to a sum n equals 0 to infinity of, let us say, a sub n times x minus x naught to the power n for x near x naught. This is what it means for a function to be analytic. It means that it's faithfully represented by a power series. All right? So it's relatively hard to come up with functions which are not analytic. I really only know of one example for you guys of a function that is smooth but not analytic. So like I'll just draw a picture of it. Like you can make a function that's 0 over here, and then it super smoothly comes in and does like this kind of thing. Right? It's something like f of x equals to 0 for x less than or equal to 0, and I think it's exponential of like minus 1 over x if x is greater than 0. So this particular function, it goes to 1 as x goes to infinity, because x goes to infinity, 1 over x goes to 0, right? And obviously it's 0 for x less than 0. And for this particular function, if you calculate its Taylor series, right? What's the Taylor series? If f analytic at x equals to x naught, then Taylor's theorem says in particular that f of x is actually equal to the sum n equals 0 to infinity of the nth derivative evaluated at x naught divided by n factorial times x minus x naught to the power n. So if a function is analytic, it is generated by its Taylor series at the point, right? This is the Taylor series. I'll write it out for a few terms here. This is f of x naught plus f prime of x naught times x minus x naught. Those first two terms are the linearization. If I put y equals to that, I've got the tangent line based at x naught, right? The next term up in the Taylor series, 1/2 f prime prime of x naught times x minus x naught squared. And then 1/3 factorial f prime 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 of x naught times x minus x naught cubed, and it's so forth and so on forever and ever, right? Unless it's a polynomial, in which case it truncates at finite order. But that's the Taylor series, right? So here's the deal. The reason that this lone example over here is not analytic at 0. Well, it turns out that if you work out the mathematics, which we're not going to work out because who wants to? I mean, I don't want to this morning. But if you work out the Taylor series centered at x naught equals to 0 for this function, you get the 0 function. Every single derivative of this function is 0. So the graph of the Taylor series, this is the Taylor series generated by f of x. It's equal to 0. The Taylor series centered at 0, let's say. So this function is smooth. I can take as many derivatives of it as I want forever and ever, right? I can calculate all its derivatives. So I can calculate the Taylor series. It's 0 at the origin. Yet the function is not 0 at the origin, right? So this function is not analytic. If you ask me for another example, all I'm going to do is take this example and tweak it a little bit. All right? Examples of functions which are smooth but not analytic are hard to come by. So anyway, now that we've got that behind us, let's talk about the major theorem of the course. So, so here's the theorem. If you have y prime prime, let's say, plus b1 y prime plus b naught y equals to g, then there exists a fundamental solution set y1 and y2, whose domain, let's say, is as large as the intersection of the domains of B1 and B0. And that still doesn't quite capture it. Let me show you some examples of how to find the domain, all right? It's like example 2. We'll have to come, and we have to, let's see here. Well, I guess this is true. What I wrote is true, but we'll really need to take, we're going to need to take a complex perspective. We're going to have to think in C to understand this. And intersection of the domains of B I should say, there's a little bit more here, which, let me say it this way, which make B1 and B0 analytic. So I should probably find the proper statement of this theorem in the book, but I left my book in my office, so you'll have to forgive me. I think it's better and better for me to illustrate by example anyway here. Maybe as I do that, I'll come to a more careful statement of this theorem. So if I have, for instance, y prime prime, I'll keep it real to start with here. Y prime prime plus, like, 1 over x y prime plus, let's say, 1 over x minus 3 y equals to, it doesn't really matter what we put over here. I guess the g does matter. My bad. But I'll just put x here, squared plus 7. There we go. All right, so I'm not going to say how to solve this problem just yet. I just want to talk to you about what the domain of the solution is going to be after we solve it. Okay, I'm just dealing with the issue of domain to start with. So what's the trouble spots? Trouble where? X equals to 0 and 3, right? So if I was to, and I guess the other thing is, I think the thing that I have failed to say yet, which is kind of important, let me put it in red. Yeah, here's the thing that's making my spider sense tingle. Fundamental solution y1 as power series. All right, so if I write y equals to like the sum n equals 0 to infinity of like some constants a sub n times x minus 1 to the n. Or if I was to write y is equal to the sum n equals 0 to infinity of b sub n times, let's say, like x minus 10 to the n, I'd have a very different story about what's the domain of the first series versus the second series. Like these are different solutions. So like here's a picture. The trouble spots are 0 and 3, right? I'll draw another picture down here. 0, 3, these are the places. The trouble spots, these are called singularities. So singularities are places where the coefficient functions are not analytic. Notice that I'm assuming a very special form of the differential equations to start with. I assumed that the leading coefficient of y prime prime was 1. That's important, because if it's not, we have to divide by it in order to get to this point. All right. Anyway, so the trouble spot, 0 and 3, right? So if I center my solution at 1, I can make the domain of the solution will be as big as it possibly can be, such that I don't get past the trouble spot. Because the thing is, do you guys remember from Calc 2 what the domain of a power series looks like? Remember, it's got a radius of convergence, it's got an interval of convergence. They're always symmetric about the center of the series. So I'm forced for the domain, the open interval of convergence is going to look like this. It's got to look like that. So basically, this is going to converge the whole thing, not just that inside part, of course, but the series is going to converge for what? Something like 0 less than x less than 2, right? As you may recall from Calculus 2, and same thing happens here, it may or may not be the case that you actually do converge at 2. I think 0 is probably not going to be a place where we can converge either. Technically speaking, I really can't solve the problem at x equal to 0 because the differential equation is not defined at 0, as I presented it here. All right? If I was to instead have presented this differential equation, see, there's another way to look at this. I could have multiplied this by x times x minus 3. See this? So this is not, obviously this is not quite the same differential equation, right? I mean, they're very much related. But to be fussy, I would say that 0 and 3 are in the domain of this differential equation, right? But they're also weird points for that differential equation. They're called singular points for the differential equation. If your differential equation is written this way, if you make the leading coefficient of the differential equation 0, that makes it a singular point. it's not really a second order differential equation if you do that, right? So things break down in that regard. But anyway, so 0 to 2, we can be sure that that open interval of convergence would be available for the domain of the function, the solution expanded at 1. How about the other one, though? What's the trouble for that one? See, we got 10 over here somewhere, right? And so if you center your solution at 10, then the domain has to be symmetric about 10, and the first thing you get into trouble with here is 3. See? So it would go something like what? 10 to 3 to, what's over here? What's the radius of convergence for the solution here? This distance, 10 minus 3? 7. So this would be what? 17, right? So we can, this case right here, you know, we would know that it converges on, you know, 3 to 17. It might do this. It might actually do this. I don't know, without, you know, further analysis. Although again, to be fussy, I would say that I cannot include 3 for this differential equation, whereas I would be comfortable with including 3 for that differential equation. They're different by those 2 points. All right, that's one example. I'll do one more of these examples, and then we're going to leave this behind us. So, at least for today. If I had, let me do it over here. If I had something like x squared plus 1, well, let me make it more exciting. X squared plus 4x plus 5, y prime prime, plus, I'll just keep it simple, y prime plus xy equals to 7, right? To understand, you know, so the question I'm asking is, if I write a series solution to this problem, what domain do I expect for the series solution, right? I'll repeat that again. So the question is, if we solve with y equals to the sum n equals 0 to infinity of a sub n times x minus x naught to the n, then what domain can we expect for this solution? All right. So to understand that, I first take the differential equation and I rewrite it like this. Oops. So I divided by the leading coefficient. Now I have it in the standard format to like draw, you know, to use my easy theorem here. Well, relatively easy theorem. Then the question is, you know, where, so basically the question boils down to this. Where is 1 over x squared plus 4x plus 5 not analytic? And so the answer here, we just, unfortunately, I can't help it. You know, sometimes real questions beg complex analysis, and this is one of those. We have to think of this as a complex function to understand where it's singular. All right? So this we can rewrite as what? 1 over x plus 2 squared plus 1. Which, if you like, you could rewrite as 1 over x plus 2 plus I times x plus 2 minus I, right? So we have division by 0 where? x equals to minus 2 plus or minus I. And to figure out the question that I've posed in this question, we have to draw the complex plane and understand the domain in terms of how power series work for complex variables. In complex variables, a function's analytic means that it converges on a disk in the complex plane. So the radius of convergence becomes an honest-to-goodness radius of convergence and all that. But let's just point out that our singular points, they always come in conjugate pairs because we're working over the reals. But you got minus 2, right? And then there's a singular. I usually use x's for the singular points. There's an x down here and down there. So this is minus 2 plus I is my one singular point. Minus 2 minus I is my other singular point. Notice that x naught was a variable in the statement of this question. So typically if I ask it on a test or something, I would actually specify, find x naught. I give you like a couple different values of x naught to figure out if you understand the theorem or not. So here, you guys can give me whatever you want. I just only insist that the x naught be real because that's where I ask the question. Okay, I don't ask you what's the domain of the solution at a complex point. That's outside the scope of this course. But I'll get us started. We could have x naught equals to minus 2, for instance, right? If I center my solution, if I write y is equal to n equals 0 to infinity of a sub n times x plus 2, quantity to the n, well, this would be a power series solution centered at minus 2, right? Where does this get into trouble? Well, the center's here. Where's the first trouble spot? Above and below, right? So if you can see it, the closest singularity there, of course, is, well, they're both the same closeness, aren't they? So this would be the disk of convergence, something like this. How far is it from minus 2 to minus 2 plus or minus I? It's distance what? Distance 1 from minus 2 plus or minus I, right? So I would, my domain includes what? Apparently minus 3 to minus 1. All right? Let's try something a little bit more interesting. Like, what if we looked at the power series solution centered at like 3? Right? Over here at 3. X naught equals to 3. So then I'm asking the question, if I write my solution as the sum n equals 0 to infinity of like b sub n times x minus 3 to the n, what's the domain includes here? Again, the endpoints of the domain would require separate analysis, and we're not going to get into that today, at least. So this, 3 is distance what? You guys tell me. From minus 2 plus or minus. It just so happens that 3 is also the same distance between both of the singular points, right? I think that always has to happen pretty much. Unless I had unless I had more interesting singular. You could have more than one troubling thing, and if I threw in additional, we could have trouble in more than one spot. More than 2 spots is my point. That could spoil the symmetry. But here, since there's just these 2 conjugate points, they're both the same distance. What is that distance? This triangle is what? Height is 1. How far is this?
5.
I heard a 5. 3 minus a minus 2? 5, very good. So what's the length of the hypotenuse? Square root of 26, very good. So the domain includes 3 plus or minus 26, square root of 26. So the domain includes 3 minus the square root of 26 to 3 plus the square root of 26, all right? Okay, so the first point of order is just I want to explain to you guys, as we're solving differential equations with series, what do we expect in terms of their domain? Like, this is what we expect. It's not just what we expect, it's what has to happen. there's a continuation theorem that says that the solution, if if there is an analytic solution, it will extend into the next singularity in the sense I've described today. So that's kind of cool. However, if we were not using power series solutions, if we were using something else, then this theorem no longer applies. But if we're looking for power series solutions, then this is the case. So if the differential equation is such that the coefficients of the differential equation, right? So like this original problem, a sub 2, a sub 1, a sub 0, g, guys. If we have a differential equation with these coefficient functions, a2, a1, and a0, and g, if these are all analytic, all right. Oh, there's a fussy condition I need. It's better if I look at it this way. I'm sorry, guys. If we look at, it's easier to say here. If b1 and b0 and g, they're all analytic at the point x0, all right, then that's said to be an ordinary point of the differential equation. And if we have an ordinary point of this differential equation, then we can write the solution as a power series on some neighborhood of such a point, all right? And how big a neighborhood? Well, that's what I'm just describing with these last two examples. So this is how the solution around an ordinary point. And ordinary is exactly like it sounds, ordinary point. Ah, come on. Son of a gun. So if we have b1, b0, g, all analytic at x0, then x0 is an ordinary point. For star. And this theorem, restated, simply says that, hey, there exists an analytic solution, a power series solution for a differential equation about an ordinary point, and that solution extends until the next singular point, the next closest singular point at least. All right. So now that I've told you a fair amount about domains, let's actually solve some of these. So how do we solve a differential equation now? Well, we'll start out homogeneous as our usual custom, right? And we're on example 3 for today. So we'll start out relatively simple. Let's look at like y prime prime plus, oh, I don't know, 3x squared y prime plus xy. And we'll keep it homogeneous here, the 0, with, yeah, that's it. And what we're going to do is we're going to find, power series solution centered at x not equals to 0. We'll find the first 4 non-trivial terms. All right, so part of this course becomes much easier because the form of the solution here is just kind of brain dead. Like you just write, oh, okay, so we're looking for a power series solution. So that means we just write the sum n equals 0 to infinity of a sub n x to the n. Why do I do x to the n? What did the problem ask for? Power series centered at x naught, right? So we do a power series centered at 0, which is this, right? AKA Maclaurin series, right? And because I'm only working for the first 4 non-trivial terms, I'm going to adopt the plus dot 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 notation. All right. There will come a time where we use the sigma notation. We'll do that next class. I'll show you how to work with the sigma notation carefully next class. That is something you need to learn. But let's start with the basics, which is this. So a0 plus a1x plus a2x squared plus a3x cubed plus a4x to, that should be more than enough. And then we differentiate this thing, right? So we got, y prime is, well, a1 plus 2a2 plus 3a3x squared plus 4a4x to the third power, Then we take the second derivative. We get 2, my bad, there's an x here, right? 2a2x. So we get 2a2 plus 6a3x plus 12a4x squared and so forth and so on, right? Then what do you think I'm going to do? It should be very, very, very unsurprising, right? What do I do? No, I do not do that. Although, I mean, I can see why you'd say that, but no. We go back, same thing we always do. We make a guess at the form of the solution, which isn't really a guess here because the problem told you to look for a power series solution. And then we plug these into the differential equation. And we see what happens. So y prime prime is the first thing, right? So what do we got? We've got, I'll write down here. Make myself some room. So I've got 2a2 plus 6a3 x plus 12a4x squared plus ... That is my y prime prime term. Plus what? Plus, let me put a red down here to make sure we, this is important. That 3x squared's got to get multiplied by things, right? 3x squared times what? Times y prime, which is a1 plus 2a2x plus 3a3x squared plus ... I think that's going to be enough there. And then I've got x times y, right? And again, my y is a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth plus ... All of that's equal to what? Equal to 0. How do you think we're going to solve this? If you have two power series, right, and they're equal, what can you judge from that? What can you ascertain? You can ascertain that they have to, every coefficient of the power series has to be equal, right? On the right-hand side, I have the 0 series. All of the coefficients are 0. On the left-hand side, I have a more interesting series, right? So we can look at order by order. Constant terms, what do we got? We've got ourselves a 2a2 for the first. Where else do we have constants? Not here. Not here. That's it. 2a2 equal to 0. How about the x terms? What do we got there? Where there we've got 6a3 here. Can I have an x term from the middle term? No can do, right? And how about over here? Can I, just a naught, right? So this is equal to a naught. Those are the only linear terms, right? What about x squared? (12a4), yeah? Plus 3a1. Anything else quadratic? How about over here? x times x, I get plus a1 again over here. That's equal to 0, right? Did I say equals to a naught? Seriously. No. What's this? You guys got to stop me. Come on. Plus a naught equals to 0. All right, there we go. How about x cubed? What we got for x, or x cubed? Got ourselves, oh man, I didn't write enough here, did I? What's x cubed at? Where are my x cubes at here? So you got to be watching out for this. If you're missing a term, you got to add it. You can't just, oh, I didn't write it down, so it's not there. No, you got to extrapolate the pattern. So we would have, this was 3 times 4, the next is 4 times 5. So we'd have 20 a5 x cubed. The next term here is 20 a5 x to the power cubed, right? So I got 20 a5 in here. And over here, I've got a what? 2 times 3? 6, right? Plus 6a2. Anything else? That's it for there. And then over here, x to the power 3, x times x squared, we get a plus a2. All right, what's next? X to the power 4, right? So I think the next term that I haven't written here would have been what? 4 times 5. Next is 5 times 6. 4 times 5? 5 times 6. Yeah, 30, right? X to the power 4. So we'd have a 30 a6 plus, what's my x to the 4th term in here? 3 times 3, 9a3, right? Any x to the power 4 over here? a3, yeah, plus a3 again. All right, that's all I'm going to do. So can we solve these equations? I think we can, right? Order by order. There's a system, there's a pattern. So the pattern is pretty easy to see. First of all, we have a2 equals to 0, right? From this one. And if a2 is equal to 0, what's that say? Yeah, which implies a5 is equal to 0 from this guy right here, right? Okay, so we got a2 is 0 and a5 is 0. Great. What else can we say? We also have that a3. Let me write the next one in purple here, if I can get it. Purple, purple, purple. This right here tells me that a3 is equal to minus a sub 0 over 6. All right. That's actually as far as that can go. That's good. All right. So what you want to do with these problems is you want to write the higher coefficients in terms of the first two, or in terms of the lower ones, right? So a3 is minus a 0 over 6. And how about this one here? That tells me that a4 is equal to what? Here, I'll make a step. Minus 4a1. I think you're right, but I got to do the math. So you said minus a1 over 3. Yeah, I think I agree with that. I think I agree with you. All right. And so far we've only used we've only used up to the cube. The 4th power, what would that tell me? What's this last equation tell me? A6 equals what? Negative a3 over 3. But what was a3? A0 over 6, right? So this is actually equal to a0 over 18, right? So let's put it all together. I'm going to erase my homogeneous comment up there. So we find that y is equal to a0 plus, well, minus a0 over 6 x cubed, and then plus a to the fourth, x to the fourth. Oh, my bad. I'm sorry. Let me try this again. I'm trying to put them in order. So the next one was a1, right? Plus a1, a1x. a2 was 0. The x squared term was 0. Then minus a0 over 6 x. That's my cube. a3. a4 was minus a1 over 3 x to the power 4 from this one. And then 5 was x to the power 5 was 0. And then we had plus a0 over 18 x to the power 6, and then plus dot, 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 dot. But you shouldn't leave your answer like this, right? We should leave our answer like as follows. This is a sub 0 times 1 minus 1/6 x cubed, right? Well, apparently plus 1/18 x to the power 6 plus dot, 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 dot. And then plus what? Plus a1 times what? X minus x to the fourth over 3, or 1/3 x4, x to the power 4. And that's all I got for the a1 terms, right? The next term is going to be order what? You see the pattern? They're skipping 3, aren't they? Yeah? I think they're skipping this 1 to 3. Yeah, the pattern's kind of funny. I think the next thing up there is probably x to the 7th, maybe. I don't know. It doesn't matter. Have I answered the question? Yes, I've answered the question. The question was to find the first 4 non-trivial terms. So I could have got full credit for this question. I did more than I needed to here, right? I did more than I needed to. The first 4 non-trivial terms, what I mean by that is just this business right here. Those are the first 4 non-trivial terms right there. So understand what we're looking at. This is my y1. This is my y2. What's the significance of a sub 0 and a sub 1? What does Taylor's theorem say about the coefficients? What is this? This is y of 0, right? What's a sub 1? It's y prime of 0. So this solution actually, if you want to understand it, is actually written in terms of initial conditions. If you make the identification that a sub 0 is y of 0, and a sub 1 is y prime of 0. So I hope the method starts to be clear. The method, and we'll do more of these next time, but it's just this. We take the differential equation, we assume the solution is a power series, we plug it in, and we work it out order by order. And sometimes we're just looking for the first few terms, but other times we'll actually find the so-called complete power series solution. I'll show you that next time. But I got to give you back your test, so I'm going to stop here. So.